Hello, hello. Good afternoon to everyone on the East Coast. Good morning to everyone else, or wherever you're at. Hello, good day. Glad you could make it. My name is Matt Smetana. I am the Community Engagement Coordinator for the Cheshire County Conservation District. Cheshire County's in the southwest corner of New Hampshire. Have a lot of woods here, small diversified farms, a lot of veggie producers actually operating on pretty small land. And today we're going to be talking about high tunnels, greenhouses, and how important those are for season extension. A lot of our veggie farms rely on tunnels for expanding their production and just making ends meet. And up here in New Hampshire, it's cold a lot of the year. We're in the northern part of our continental US. And so it becomes really important to have a longer growing season if you can. It means making sure that you can produce enough food for the community and run a viable farm business. So we're glad you can make it. As I said, I work for our conservation district, and wherever you are in the country, you have a conservation district. We operate based on counties. We complement federal resources like our local NRCS offices. We help protect natural resources like soil, water, wildlife, and also work a lot in farm viability through education workshops and webinars like this, through grants and stipends, through equipment rentals. And our conservation districts do a lot of work for our community. So if you haven't explored what yours does yet, I encourage you to. The National Association will have information for your county. So before I introduce our fantastic speaker, Chris Lent, I'd like to just cover some ground rules for today's webinar. So today we'll be focusing on some slide presentations and potentially saving some time at the end for your questions. If you have any questions, I'd love for you to make a note of those. You can put them in the chat. Both myself and my colleague Amanda will be monitoring the chat and just keeping an eye. If we do not have enough time at the end to answer everybody's questions, we will be recording those and sending those to Chris for a follow-up. And speaking of a follow-up, we'll be including an email to you all with the recorded version of this webinar, with the slides from today, and other helpful resources to get you started. So this webinar is actually a part of a workshop series. It is funded in part by the Specialty Crop Block Grant, which was acquired by the New Hampshire Department of Ag, Markets, and Food. We're glad that you're able to join our first of a few webinars, and we'll talk about those a little bit later. But without further ado, I'd love to turn it over to our presenter, Chris Lent. Actually, first, let me tell you about Chris. He is a fantastic educator. He is an agricultural specialist based in Pennsylvania. He works with the National Center for Appropriate Technology. You'll hear about them in a little bit. He's a part of our Northeast regional team and operated an organic farm for 10 years and worked in the fields of energy efficiency, solar installation, and organic farm inspection. His work at NCAT is focused on farm energy, organic veggie production, local food systems, high tunnel management, and urban agriculture. So he is well-versed in the energy efficiency of tunnels and agricultural operations, and it's just a fantastic resource for you all today and into the future. So without further ado, turn it over to Chris Lent.
All right, thank you, Matt. I appreciate that introduction, and thanks everybody for joining us here. Thanks to Cheshire County Conservation District for hosting these and funding this series of webinars and field days that I'll be involved with them. I appreciate everybody being here, like I said, and we're going to talk today about high tunnel energy efficiency. I wanted to go over briefly first, kind of an agenda for the talk, for the webinar. And I'm going to advance to that here and want to talk a little about NCAT, just a slide or two on NCAT, which is the National Center for Appropriate Technology, and that's the organization that I work for. And then we're going to go into the elements of a farm energy self-assessment and what that looks like, and what that means for assessing your energy usage on your farm and in your high tunnels and greenhouses specifically. We are focusing on high tunnels today, but we're going to talk a bit about greenhouse efficiency as well. And that leads us into equipment in those structures and controls for that equipment. And also we'll talk then about the materials that are involved in the construction of those houses that we use to grow our crops in, and how that affects the energy usage in those systems. And then we'll talk about some of the design factors and, along with the design factors, the orientation of the tunnels themselves and shading issues. And then we'll finish with some air sealing and insulating information for those structures. And throughout, I'm going to have resources for you, hopefully, that you can turn to dig a little bit deeper into the subject matter that we're going to be covering. And so without waiting here, we're going to go forward to talk just a touch on NCAT. The National Center for Appropriate Technology was formed back in the late 1970s, so we've been around for quite a while, and they were formed to kind of help folks during the energy crisis of that time. And we were using the principles or adopted the principles from the appropriate technology movement, which were small scale, simple, local and low cost, and environmentally sound. And we still use those principles in our programming today. And there's two main sides to our work at NCAT. One is agriculture, and we do that mostly through our ATTRA project or ATTRA program, which was formed in the mid-'80s. And through the ATTRA project, we have over 300 publications available. We offer technical assistance from our specialists across the country, so one-on-one technical assistance. And there's podcasts and tutorials and video logs and all types of information on sustainable agriculture subject matter that you can access through our website, which is down in the lower corner of the slides. Each slide has our ATTRA website on it. And the other side of what we work on is energy. So we do energy audits and energy assistance for folks across the country as well. And I'm kind of here to talk about both of those things, kind of bringing those two things together to talk about energy efficiencies in high tunnels and greenhouses. And what we wanted to target today, or who we wanted to target, were folks who have like a smaller diversified vegetable operation and grow some of their own seedling starts in the propagation house. They possibly have, we were thinking people who have a high tunnel or two that's heated, along with a small greenhouse for that propagation of seedlings, and maybe to grow some starting plants for other farms in the area. That's kind of how I organized the talk today, around that type of a grower. But I think there'll be information in here for those who are bigger than that and those who are smaller. There's not a lot of information on that size farm as far as energy use, but on a larger scale picture, the horticultural industry, this is what the horticultural industry in general looks like as far as energy breakdown. So after the first two highest costs of labor and planting materials, energy is the third highest costs for those types of producers that are running greenhouses basically in this country. And of the energy costs, heating is the biggest portion of that cost. You can see in the pie chart, it's about 75% of their costs. Electricity is about 15%, and the rest falls into fuel and transportation for other equipment on the farm, or transporting things to market and those types of things. So I think this approximates what the breakdown would be of energy use on the type of farm that I was talking about earlier, with a diversified vegetable operation with a greenhouse. You may have less heating costs and a little more electricity costs, And we're going to focus on electricity today, mainly, but we're also going to kind of bleed over into some of the energy use as far as fuel is concerned and heating costs too. So, so what's a high tunnel? This is a good definition, or original definition of a high tunnel was a low-cost season extension structure covered with layers of plastic and usually passively heated or vented. So no energy inputs whatsoever was the original intent of high tunnel production. And that would be this picture down here in the left-hand side of the screen. That would be a no energy input high tunnel. And then moving to a high tunnel, farmers have now added a lot of electric inputs or energy inputs into their tunnels. So this central picture is a tunnel from a farm in New Hampshire, and they've got a heater in the backside there, a propane heater on the back wall. And they've also got ventilation fans, roll-up sides, end wall ventilation. So there's more energy inputs going into high tunnels than used to go into high tunnels in the past. So that's why we're starting to focus on the energy use more in these structures. And then if you look to the right side of the screen, you'll see a more energy intensive greenhouse production. This is a hydroponic greenhouse production, a larger scale. So you've got water pumping in addition to the ventilation and heating and so forth. So that's on the high end of the energy use spectrum. We're going to be focusing on the tunnels here in the center with maybe an additional greenhouse on the farm to raise seedlings for transplanting out. I always mention the High Tunnel Initiative from NRCS, National Resource Conservation Service. That is a initiative for helping pay for high tunnels for your farm. So that there's a link here in the presentation, but there's also a link, a series of links to resources that Matt is going to drop into the chat that I'll be mentioning. I'll be referring to those resources throughout the presentation here today. So you'll have access to those. So why are we looking at these, the energy issues surrounding these tunnels? Mainly to reduce costs. That's one of the main focuses to identifying energy use and reducing it and improving efficiencies. You could also use the information you're learning today to, prioritize project upgrades on your farm and also to improve operational efficiencies. And that mainly comes into play with more efficient controls of the systems that are working inside these tunnels, like ventilation systems and heating systems. If you're controlling them more efficiently, you're saving labor to a large extent. So there's where it could benefit you operationally. And then also, if you're farming in a sustainable manner, trying to farm in a sustainable manner, trying to reduce your carbon footprint, this is one way to do that as well, to reduce your energy use. Most likely, if you're using energy, it's coming from a carbon source, and to reduce that usage, you'll be reducing your carbon footprint. So I'm going to start out by going over, you can hire an energy assessment of your farm, an energy audit, a professional audit, but there's a lot you can do before you have to go that route. You can do a self-energy assessment of your farm. And what that involves is, first of all, reviewing your electric bill and understanding your electric bill and how that works. And then you want to go to listing the equipment that you have on your farm that's using energy, and get a comprehensive list of everything that's using energy, and try to estimate what it's costing you to run that equipment. So in order to do that, you need wattage and run times, estimated run times, and we're going to go over in a couple examples of that. But you'll be looking at things like heaters and water pumps, blowers and ventilation systems, your fans for those systems, heat mats, germination chambers, all of those things that use electricity or fuel to some extent. And you want to find out what they're using and how much it's costing you to run those things. And then finally, we're going to talk about inspecting for air leaks and insulation values on the materials that you're using to build these structures, high tunnels and greenhouses. So we'll start with energy bills. I want to go over this as an example of an energy bill. There's a lot of things you can glean from your energy bill. You can see annual highs and lows of usage. You can do comparisons between years and months of energy use. You can also figure out what you're being charged per kilowatt hour. That's an important rate to know. And then I want to show you how to figure your real cost per kilowatt hour, which is different than the rate that most utility companies are telling you you're paying per kilowatt hour. So I'll point to this. If this pointer that this laser pointer bothers you in any way, let me know. But I like to highlight things a little bit. I've highlighted this bar chart here, and through that you can tell when energy usage has gone up, because it tells you monthly how many kilowatt hours you've used, and gives you a bar for each month. So if you see something jumping, like this bar is jumping here, you want to make sure that you know why that's happening. And it's pretty straightforward probably on this bill to figure out. During the warm months, it's probably air conditioning that's causing that jump. But if you see a jump like that, you should be able to ground truth that with what's going on the farm, and make sure you know what's come online to account for that increase in kilowatt hour usage. Also, you can use this chart to compare to previous bills to see what's happening from month to month and year to year as far as changes in your electric usage. So that's useful. And then on the other half of the bill, the bottom or the back side of the bill, there's a couple more pieces of information I want to point out to you. It gives you your total usage. On this example, it's 750 kilowatts. It gives you the cycle, so you're on a 30-day cycle on this bill. Most utility bills, electric utility bills, are on a 30-day cycle. And it also gives you your rate, which I've circled here in the center. It's telling us, if you can see that small writing, it's telling us that they're charging you 8 cents a kilowatt hour, 8.8 cents a kilowatt hour. And so for 750 kilowatts, that's 66.20. But that isn't your bill. Your bill is 153 in this example. So you have to take into account all of these delivery charges here. And that's what I mean when I say the real cost per kilowatt hour. You want to take your total amount due for service during that period and divide it by your total kilowatts that have been used during that period. And that'll give you your real rate. I call it the real cost of what you're paying per kilowatt hour. And with that, we can figure out what different equipment is costing you, and we'll give a few examples. But just to be clear, your kilowatt hours can be found here under current usage, and your total charges can be found here at total charges. So you need those two pieces of information, and you can figure out what it's costing you per kilowatt hour. That's important. We're not going to do too much math here, and we're not going to have too many slides of math, but this is a very important one, because it will actually give you the ability to look at your appliances, look at your equipment, and see what they're costing you to run. I want to give you this formula. You're going to try to find the wattage rating on your appliance, and then you multiply that by your hours that you've used, and you estimate the hours you've used that. You know your equipment, you know how much you've run it. You can give a pretty good estimate of how long you've used that in the course of a year. And then divide that gives you your watt hours. You divide that by 1,000, because we're going to work in kilowatt hours, and that gives you your kilowatt hours consumed. So we'll give a good example here of a end wall fan. If we're looking at this fan that's in the picture, let's say it's using just over 11, it's using just over 1,100 watts, and you times that by 2,000 hours that you've estimated that it runs during the year, and divide it by 1,000, it'll give you your kilowatt hours used. And then if you multiply that by the 20-cent rate that we figured out, the real rate that we just figured out, it's going to cost about $450 to run that fan for a year. And if you have 2 or 3 of them or 4 of them, you can easily do the math to see what those fans are costing you to run in a year. So that's how you go through your appliances one by one, list them and see what things are costing you. It's important to know that. If you can't find a wattage rating on the nameplate of the appliance, you can only find horsepower, for instance. Then you can use this this figure here. 1 horsepower equals 745 watts, and you can transfer things into watts. If you can only find volts and amps, you can multiply them to find watts, and then you can continue with figuring with the rest of the formula and figure out what it's costing you to run. So I mentioned nameplates, equipment nameplates, and you can get a lot of good information by looking at your equipment nameplates. It's going to give you the general information about the product, but you're also going to get on a heater unit like this example. This is the back of a heater unit where the nameplate is. It's going to give you the BTUs of that. It's going to give you both input and output BTUs. And based on that, you can actually figure the efficiency of the unit. You divide the output BTUs by the input BTUs and get an efficiency. This one happens to be about an 82% thermal efficiency for this heater. That's pretty common, but those BTUs are listed right here, if you can see my pointer. You know, I should have gotten a nameplate without a wire going across the back. I'm sorry about the picture, but we can see the information we need here. You also, on fans and ventilation equipment, you're going to see cubic feet per minute listed. That's an important bit of information to figure out the efficiency of fans. You're also sometimes going to see on motors, you're going to see horsepower ratings. So I showed you in the last slide how you can use that to get to wattage and figure out how much it's costing you to run a motor like that. And then in this example, people don't think of heaters having an electrical component, but they do. They have a blower on them most of the time. And if you see over here, we have amps and volts, 115 volts and 7 amps, 7.15 amps. You multiply them together to get watts, and that's what this formula here is doing. And then I'm going through the rest of what we learned in the last slide and just multiplying the number of hours used times watts and dividing by 1,000, and we can figure out it's going to cost $177 a year to run this heater. So these are the starting point for giving yourself information on what equipment is costing you the most to run and where you might want to put your energy and effort and money to improve efficiencies. You can buy higher efficiency appliances. You can improve the efficiency of the structure, as we're going to talk about later, to reduce the cost of running this equipment. This is a good resource, and it should be in the resources that were dropped in the chat. This has to do with understanding nameplates on various pieces of equipment and how that information relates to energy usage. So that would be a good one to delve into for a little more information on that. I mentioned upgrading to a higher efficiency appliance or piece of equipment. This is an example of that. The heater that we just looked at was an 82% efficiency. This type of a heater is a high efficiency closed combustion condensing type heater, and they're 90+% efficient on these thermal efficiency. So if you've got a greenhouse and you're running a heater for long periods of time during the year, there's generally like a 2 to 3 year payback to investing in a higher efficiency heater based on the fuel savings that you'll find. So I wanted to show you what a unit like that looked like, and that has to do more with heating. Of course, there's a little bit of electric associated with running these, but that's going to save on your heating costs to a large extent. So let's talk about some of the other equipment that's used in high tunnels. These are horizontal airflow fans. They're used pretty pretty consistently and ubiquitously to keep the airflow moving inside of the tunnel. If these are run for a large part of the year, 4 of these fans can easily cost $1,000 a year to run, to operate. So it pays to look at some efficiencies with these fans. You want to properly size them. And the rule of thumb there is you want to size them to about twice the area of the space or the structure that you're trying to move the air around in. So for an example, you've got, if we had a 30 by 60 tunnel, you would get the area of the tunnel by multiplying 30 by 60, and you'd times that by 2 times that, and that's the amount of cubic feet per minute that you would want the capacity of the fans to have. So if you're using 4 fans, you could divide by 4 and have 900 CFM fans, and that would give you a proper size to do the job right without oversizing the fans and using extra electricity. You also could look for fans that are slightly lower horsepower, somewhere in the 1/10 to 1/15 horsepower range, with larger diameter blades. They tend to be much more efficient and will use quite a bit less energy than a fan that has maybe a 1/8 or 1/4 horsepower and is lower diameter blades. So they cost a little bit more money up front, but when you have a rate of 20 cents per kilowatt hour, they will pay for themselves over the course of several years. Maintenance is important with this equipment as well. And what I mean by that is keeping the blades clean, keeping the cage that's around the blades free of any kind of obstructions, so it's not hindering the airflow. Those are important things to do once or twice a year so that they're running as efficiently as they can be running. An easy way to do that would be to take a small air compressor and walk around with your step ladder and go up to each one and kind of blow them out, blow the dust off them every couple times a year. That's an easy kind of efficient way to keep them fairly clean and operating a little more efficiently. But your best bet is to shut them off and try to utilize natural ventilation whenever you can. And a lot of growers are moving to this. Most growers are doing it now with sidewall roll-up sidewalls and in-wall vents. But to do it properly, there's a few things that we're going to talk about as far as natural ventilation in a slide or two here to do the job right with natural ventilation. First, we're going to look at another appliance, this blower, this squirrel cage blower, which blows a layer of air in between 2 pieces of plastic. Now, it's fairly essential to have a double layer of plastic if you're heating a high tunnel or a greenhouse structure. You want 2 layers of plastic over the structure with an air layer blown in between the 2 layers to create an insulated space, kind of a dead air space of insulation. And to do that, we use these, what they call squirrel cage blowers. And you have to size these properly. These aren't going to cost you a lot of money. They run 24/7, pretty much all year long, but they still are very efficient, and they usually won't cost more than $100 a year to run one of these units. But it still pays to size them properly, so you're not paying more for them than you'd have to. And the general rule of thumb there is, if you're trying to inflate a square foot area of under 2,400 square feet, you're going to use a 60 CFM blower. And if you're going above that threshold of 2,400 square feet, you move up to a 148 CFM blower. And those are the 2 most common sizes that you'll find out on the market. So that's why I'm using them, using them as an example, the 60 and 148 CFM. Again, they won't cost you that much to run, but it does pay to keep them clean. I use old toothbrush usually to scrape out the blades inside the air inlet. and then I vacuum them, take a vacuum and vacuum that out. You want to be pulling air from the outside for these, and there's a couple of reasons for that. This one in the picture is shown pulling air from inside the tunnel. And what that does is usually the air in the tunnel is more humid, more moisture, and you're blowing condensation in between the two layers of plastic. If you get condensation in there, it blocks the sunlight. And the less heat gain from the sun, the more you have to make up with energy inputs in that tunnel. And the second reason you want to pull air from the outside is when you pull air from the tunnel itself, there has to be makeup air from somewhere, and that's going to come from outside the tunnel through cracks and leaks in the structure. So you're going to be pulling cold air into the tunnel. And so those are the two reasons why you buy a kit, a small tube that hooks onto this inlet, and then the other end goes to an end wall, and you pull air from the outside to supply these. You can use spacer blocks, plastic spacer blocks, and shut these blowers off altogether. A couple of problems there is they don't provide, I think, the 8 to 10 inches of airspace that you want to look for in between your two layers of plastic, and they're a little expensive and they're hard to find. I have a source for them though, if you're interested, and you can contact me if you are interested in spacer blocks to do the job. So as far as these sidewall ventilation fans, and these might be larger than the ones you're used to using or seeing, or maybe not. Maybe they're about the size you have on your farm. These can be very expensive to run. You could be looking at about $1,000 a year if these are running a lot of the year. Which in a larger scale greenhouse operation like this, they oftentimes do. So it becomes pretty important to look at efficiencies with these. One thing to do is size them properly. For warm season ventilating, you want to look at about 1 air exchange per minute for the entire structure. And so that's moving a lot of air. For cool season and winter ventilation, which is done more occasionally and might be more of what you're used to using a sidewall vent fan for, you want to look for 1/4 to half the volume of air exchange in the structure per 1 minute. And that's based on cubic feet per minute. And so you want to size the fan so it's able to do that. But not get a bigger one than you actually need. You look for the ventilation efficiency ratio of higher than 15. 15 or higher is considered fairly efficient fan. That's a function of the cubic feet per minute divided by watts. Or you can go to the Bioenvironmental Structures System Lab at University of Illinois, where they have an online database, and they do testing of all kinds of agricultural fans, and they'll list the efficiency ratios there and the CFMs and other things about the fans. So that's a good resource right there, and that'll be in the chat as well. Look for 2-speed fans and controllers that can control 2-speed fans, because you don't need them on high all the time. You only need them to kick in to the level that you need them, and then if temperatures continue to rise, then they can go into their higher speed. But that saves quite a bit of energy when you're not running them full blast all the time. And again, keeping them clean and maintained is important. The shutters on these need to be working freely, with no obstructions, and make sure they're closing and opening very easily so they don't obstruct the air. And make sure the motors are clean. There isn't a layer of dust over the motors, and the belts are tight. And those types of things are good maintenance a couple times a year on these larger fans. So I talked about natural ventilation. The rule of thumb for this is to be effective, you need about 15 to 20% of the square footage that you're trying to ventilate in open space along the sidewalls. that's combined on both sides. And then you need about that same amount in open space as a vent toward the top of the high tunnel. And that's why you see these large gable end vents to try to get natural ventilation going. These are a little undersized, but with the door open and the vent open, there's going to be quite a bit of natural ventilation going on here. With a little bit of a 1 or 2 mile-an-hour breeze, it can be a really effective way to ventilate. And you can shut your exterior fans off. You can shut your horizontal airflow fans off as well when you have good natural ventilation. In fact, you should shut your horizontal airflow fans off because they interfere with the natural currents that are taking place. Orientation also improves this, and we'll talk about that in a little bit down the road here. Now, as far as controllers for your ventilation systems and your heaters for these structures, I think you want to move towards digital if you haven't already. This is a digital controller for ventilation, sidewall ventilation, and like roll-up sides and fans. And then here's a system using a mechanical thermostat for sidewall roll-up sides. And this is a digital thermostat with multiple zones. It's more complicated than some need, but something similar to this, that's a digital 2-stage thermostat, would be ideal, I think, for controlling your heating and ventilation systems. The problem with these mechanical ones, this type in the middle, is they tend to be 5 to 8 degrees, or they can be as much as 5 to 8 degrees off. So if you're heating the space 5 to 8 degrees more than it needs to be heated before it shuts that heater down, for every degree you're heating, you're using 3% more energy in that system. So you can save upwards of 20% on your heating energy, at least, if you move from a mechanical thermostat to a digital thermostat. And you're improving some efficiencies here too, because you can control your systems, to within 1 degree of a set point with a digital thermostat. And sometimes you can monitor these from your phone to see what the temperature is in your high tunnel and so forth. So it's a big improvement. They're more expensive, but they can help with energy savings, and they can help with the efficiency of your operation. So let's talk a bit about materials. The common glazing materials or covering materials for these structures are 6 mil greenhouse plastic, but there's some things you need to have. There's a few treatments for these that are very common now, but I always try to mention them because they're extremely important. Infrared treatment on the inner layer of plastic is going to be very important, because that prevents infrared radiation from leaving the high tunnel at night. So this alone in a heated tunnel situation or a heated greenhouse situation can save about 20% of the cost of heating. So that's a very important energy saving treatment there. And then the anti-condensate prevents condensation from forming and staying on the inside layer of the plastic. So what that will do, if you have enough condensation, it'll block sunlight and reduce the heat gain from the sunlight, and you have to make up that heat gain with added energy inputs, meaning your heater has to run longer. So those two treatments are extremely important. Polycarbonate is another very common material that's being used. It's more expensive than the greenhouse plastic, the poly greenhouse plastic, but this is what it looks like installed, and it's used on end walls quite a lot now. This is only up 4 feet on this particular high tunnel. I like to see the whole side covered with poly. The R value, which means the resistance to heat transfer on the polycarbonate, is about 1.6 R. And that's about the same as 2 layers of plastic with an air pocket blown in between. So you can match the double layer of poly on the top, you can match that R value with using polycarbonate on your sidewalls and have about an R 1.5 on the whole structure. Oh, one thing I wanted to mention, when you put the polycarbonate in, you see these air gaps or these channels. You want to make sure you close them up with tape, put a piece of tape over these or caulking or somehow close them up. Otherwise, you'll get air movement up along these and it'll reduce the R value rating. So before you install, make sure you seal the edges. If you want to look into more glazing materials, there's a great resource that we have, the Sustainable Season Extension Considerations for Design. This is a ATTRA publication, and you can access it through this link, which will also be dropped in the chat with the other resource links. And this is one of the quick references in there showing you the R value of different materials. So there's a lot of good information in this pub, and if you want to delve a little deeper into the energy efficiency of different materials, this would be a good resource for that. Now, this is an older drawing, and I realize it's not the neatest drawing in the world, but the work that Steve Moore did here in Pennsylvania years ago, he was working with unheated tunnels, but he was able to put efficiencies in the tunnels that would give him growing conditions. As you see here, he's saying he got plus 22 degrees over nighttime minimums inside these beds. So anytime you can improve efficiencies with the high tunnel to reduce the amount of heat you have to put in the tunnel, I think it's worth looking at. And what he was doing here is he would do sidewall insulation with rigid insulation board. He also buried insulation board on a slant along the perimeters, around the perimeter of the tunnel. He would put insulation also underneath the walkways. You see a small area there insulated. He doesn't draw it here, but there's 2 layers of plastic he's indicating with air blown in between. And he's also covering these beds with some type of thermal covering, either row cover, or he liked to use old greenhouse plastic. And that's how he was getting those efficiencies inside the high tunnel. And so it's worth doing these things to, if you're getting those kind of temperature increases over your nighttime minimums, you're going to have a lot less heat input if you're heating a tunnel to try to keep things above freezing, for instance. That heater is going to turn on a lot less frequently if you have these types of efficiencies in your tunnel. As far as greenhouse efficiencies, there's certain things you can do there too, and that's insulation does come into play here as well. But your orientation's important, and I'll have a visual for that in a minute. You want to get as much heat gain from the sun as possible, so that's where orientation's important. You don't want any shade for the same reason. Of course, that double layer of inflated plastic is very important. You can see it here in this picture as these plastic kind of billows in between the ribs. That's 8 or 10 inches of dead airspace that's providing insulation inside this greenhouse. And this greenhouse happens to be at Dog Days Farm up in New Hampshire, and we are going to have, as part of the series, a field day there in the end of March, I believe the 26th of March, where we're going to go and have a field day where we can talk about these same issues and see some of them in action on his farm. So keep that in mind for sure. You also want to right size your greenhouse space. You don't want to be heating space that you're not using. That's what that comes down to. You want it well drained because if you have water flowing through, it's going to pull heat out of the tunnel, and you're going to make that up with energy input, with heating energy input. You also want to look at insulation here, like we did on the high tunnel efficiencies in the last slide. You could go up to the knee wall here, up to the hip board rather, with insulation on the north side, and up to the height of the tables on the south side, because you don't want to cause shading on that side. And some of good materials for that would be a foil-faced bubble wrap. It's not cheap, but once you make the investment, it's very durable. And with these insulations, there's usually a payback with a heated greenhouse space. There's been paybacks shown within three or 4 years on insulation investment. So if you're investing in insulation up to the top of the tabletops or the hip board, you're going to get that paid back in reduced energy costs over the next 3 or 4 years. Thermal blankets I'm mentioning, but they're mainly sold for larger scale greenhouse production systems. And that's what the blankets that are on the market and the systems that are on the market are for larger scale. And I haven't seen effective systems to put in place in this size greenhouse. I think they would help tremendously if it could be done, but it increases labor because they have to be rolled back every day. So they're not, from a practical sense, they're not really there yet, but I look forward to seeing some innovation in that realm on the smaller greenhouse production scale. This was my seedling house when I was growing, and it's not the neatest example or the best example in any way, but I was trying to show here that at least what I was doing with this plastic draped here, I would close this plastic up in the early part of the season and cut my greenhouse space in half. So I was only heating half the space for that coldest part of the year. And then as I progressed into warmer days and needed less heat but needed more space to expand, I would open them up and use the expanded space. I was also trying to use vertical space here. I was hanging shelves so I could utilize the vertical space in the structure and get more bang for my buck, so to speak. And I had the inflated 2 layers of inflated plastic, but it wasn't. I've since learned that it wasn't inflated to the degree it needed to be. I was getting about 4, maybe 6 inches in there, and you really need 8 or 10 inches or better to get that R 1.5 over the whole structure. Let's see, I'm at about 45 minutes. Okay. I mentioned this hydronic floor and bench heating because it can help in a greenhouse production system that's more efficient to heat with hydronic heating right under the bench or under the floor. And I'm sorry, the picture is not better, but this is a hydronic system back here with a water heater, propane water heater. And these are tubes going under this mat. So there'll be, trays of flowers or plants on this, sitting on this floor and being heated from below. With a hydronic heating system right on the bench or on the floor, you can reduce your set temperature for heating the whole airspace in the structure by about 10 degrees sometimes. And for every degree you reduce that, you save about 3% in energy costs. So that can be an effective way to reduce your energy use. Some of that is put into heating the water, of course, but the hydronic heating is more efficient, so you end up with a net positive of energy savings. So here's the orientation I was talking about. Here in the Northeast, or in the northern part of the country, rather, you'd want to go with an east to west on the long axis of the high tunnel if you're doing year-round production. And that's going to give you, in the winter time, you're going to face due south with this large section of the high tunnel. And you can think of that as a large solar collector, basically. So you want that facing due south. You can see the solar panel here facing the same direction. That's why I thought that was a good example. But that's going to give you the maximum heat gain that you can get for that structure. And the other reason to run it that way is if predominant winds are from the west or northwest, it's going to create a vacuum on this east gable vent that's going to help with natural ventilation. So for those 2 reasons, it's best for energy reduction to run it that way. I'm not going to spend much time here, but it's important not to have shading on your structure for the reasons I've said already about making that the heat gain of the sun as efficient as you can. But there's a really good fact sheet that'll be in the chat amongst the links that we're putting in there on how to site a greenhouse to receive the most sun. And that's an instructional fact sheet from UNH or University of New Hampshire that's going to show you how to fill out a sun chart here. And this looks complicated, but it's fairly simple. With a sun chart and a compass, you can basically chart a shade line on any part of your property. You can see where there's going to be shade during any part of the year at any time during the day. So this is a very valuable tool to learn how to use. You can learn to do this in a half hour, and you can fill one of these out, chart one of these in about a half hour. So if you're looking to put up a high tunnel or a structure that a greenhouse structure, make sure you know that there's not going to be any shading. As far as construction and being airtight, just like any structure that's heated, you want to make sure that your structure's fairly well sealed. That means a very airtight connection of plastic to the pipes and to the baseboard on the end walls. With polycarbonate, you want to make sure there's no gaps behind it if you're putting polycarbonate or another material on the end walls. This is a good example. It's a very tight foundation. The doors and windows in this one are very well sealed, very tight, and the plastic is tight to the last bow here. There's a few things that you can do to increase that air tightness. In the winter, when you close up the tunnel or the greenhouse, and you're getting ready to heat it, you can use wiggle wire channel along the bottom edge of your sidewalls and up the edge of the sidewalls to lock that plastic into place. You can do the same thing around shutters like this. This isn't actually with the plastic in place, but a shutter similar to this, you could put wiggle wire channel around it and put a piece of plastic, wiggle wire a piece of plastic over it. If you need to remove your plastic more frequently for ventilation, you could buy some heavy duty Velcro. There's exterior Velcro in 2-inch wide strips. You can buy it. It's about $1 a foot. And if you put a strip of Velcro around there and the opposite strip on a piece of plastic, you can quickly cover up your exterior openings. And if you need to ventilate, you can quickly pull them off and do your ventilation and then put them back on. So that's a good way to cover up any leaky doors or windows or shutters that are in these structures. Around the baseboard is another weak spot for air infiltration. This is me putting a metal sheeting or an aluminum flashing rather around the base of my high tunnel. It's not the neatest job, I'll admit, but you get the idea that you don't want an airspace between the ground and the baseboard. And if the ground isn't burying that, you're going to get a lot of air infiltration underneath that baseboard. This is a way to avoid that. And then look for these types of gaps behind your polycarbonate. There's about a 1/4-inch gap here that you can see behind your wiggle wire channel. There's a gap. You can put foam seal behind there, a very inexpensive, they call it, contractors call it sill plate seal. It's rolls of foam that you can cut into strips and put it behind your material here, and it would take up that gap, and it takes care of those air gaps. So that's tightening up a structure. I know there was a lot there covered. There was a lot that I didn't get to in this subject, but I want to give you some resources that we have as well. These are self-guided tutorials that we put together at NCAT. It's on all types of farm energy efficiency. So if you can go to our website, which is linked here, and pick out the topic areas that you're interested in, kind of do a self-guided tour or Tortui. Oh, can't say the word anymore, but you heard you know what I mean. It's a self-guided tour of energy efficiency subject matter on all these topics that you see here. So take advantage of that. And then as far as renewables and energy efficiency funding sources, I always mention the REAP program, the USDA REAP, which is Renewable Energy for America program, and that's run by Rural Development, USDA's Rural Development. That is a grant funding source for energy efficiency measures and alternative energy projects for farms and rural businesses. So they will pay up to 50% right now, currently, in grant funding for on-farm energy efficiency projects or alternative energy projects. There's also USDA NRCS has an on-farm energy initiative. They're mostly looking for really higher energy use farms like dairies and those types of things, but it would pay to contact your NRCS office to see what they're offering in that line. They also have out, NRCS also has out a energy self-assessment tool. That's a very interesting tool that allows you to go through and enter the equipment that you have on your farm, and they'll do cost analysis for upgrading that equipment in that tool. So that's a really neat tool to see. And then just look for programs through your universities, your extension offices. Utility companies sometimes offer energy efficiency upgrades to equipment. So look what your utility company is offering right now, and check in with them once in a while. Different state agencies in different states sometimes offer help with funding for energy efficiency measures on farms. And I also found for those in New Hampshire, there's this Community Development Finance Authority that offers energy audits. So that you might want to look into that link if you're in New Hampshire. And then also the Conservation District, Cheshire County Conservation District is having a new opportunity come up that you want to look out for. It's a $2,000 energy stipend grant opportunity for specialty crop producers. So that's something you might want to check out at the Conservation District. And then there's, I don't have two other ones in here, but maybe Matt could mention the other funding sources that are most recent.
Sure, absolutely. So along with that $2,000 energy stipend, through the conservation districts in New Hampshire, if you operate in New Hampshire, you're eligible for up to $10,000 to improve climate resilience on your farm. So saving electricity, heating, renewables, you name it, soil management, you can get up to 10 grand to implement a climate adaptation or mitigation project on your farm. We also have a local opportunity here in the southwestern corner of New Hampshire. It encompasses surrounding towns as well, to gear farms up for wholesale production. If you're not quite there yet, there's a grant that can help get you there, help you purchase equipment, infrastructure, labeling and design needs, hiring certain contractors that will just get you to that next step. And I encourage you to take a look at your conservation district's website. The programs through each conservation district are different. Some of us cover food access or recreation. A lot of us cover farm viability and have local funding sources for you. So definitely take a look at your local county conservation district and see what's available.
Yeah, thank you, Matt. Thanks for mentioning those, and I thank you, everybody. That's all I have for you, but I would take a question or two if you had them. Otherwise, I'm happy to continue the conversation through email. This is my email address, chrisl@ncat.org, and you can contact me anytime with any questions about this and any resources you might be interested in that I might be able to get to you. And so I thank you for your attention today.
Thank you, Chris. This was fantastic. We're right at 1:30. So I would say that this ends our formal presentation for the day. We really appreciate you being here. To all the folks who registered, we will be sending a follow-up email to you, including Chris's presentation. So you have access to all of the resources listed there. You also have access to the recording of today's session. You'll be directed to our websites respectively to take a look at some of these grant and education opportunities. And we'll also ask for your feedback on how it went today. Quick reminder that we have a couple other webinars that you might want to check out if you're in the realm of farm viability and looking at efficiencies. Just taking a look at some notes, but we have an agri-solar workshop coming up on January 23rd. We have an irrigation efficiency workshop or webinar. Both of those are webinars. So the irrigation webinar will be held on February 13th, and those will be included in our follow-up as well. I'll also be mentioning the on-farm workshop that Chris brought up in the presentation. That will go in the follow-up as well. So we will be recording all the questions that you had today. I'll get answers from Chris on some of those. The other alternative, Chris, I don't know if you're able to, but we can also stay on past this formal presentation time and answer some folks' questions.
Yeah, I'm able to do that if anyone wants to ask a few questions. Yeah.
Fantastic. Yeah, so we had a few questions. I'm going to go back up to Sue's. It was on the slide. If you're able to go back to the slide with the blower image of the sides being inflated. Sue asked for the square footage. Is it based on the footage of the ground the high tunnel sits on, or the actual square footage of the high tunnel walls?
It's based on the square footage of the area you're trying to inflate. So it would be the whatever area the double wall of plastic covered.
Great.
So that's the answer to that. Yep.
So it's the square footage of the tunnel space itself.
The actual, like the roof of the tunnel, the area of the plastic that you're trying to inflate. So up over the top of the roof, the area you're trying to inflate.
Gotcha. So it's all the whole plastic all the way around. Fantastic.
Exactly. Yep.
So Raj asks, what distance ought there be between the layers of plastic? I think you answered that later in the presentation and said 8 inches, correct?
8 to 10 inches, I think, is what you're shooting for. That requires you putting on the outside layer a little looser than you would think you needed to.
Great. Yeah. Thank you. He also asked, if temp is right, how and why is CFM for airflow important? Is CFM dependent on temperature?
I'm wondering if that's for all the ventilation of the entire tunnel you're asking?
Raj, if you're here, would you want to speak up and clarify?
Yeah, I'm just trying to see if your temperature is okay. How important is the airflow?
Well, the airflow there's two things you're trying to control inside the structures is temperature and humidity levels too. So, and usually humidity is controlled along with temperature, because as your temperatures are dealt with, you're also moving air through the structure and getting rid of humidity. So it's most of the time dealt with at the same time. But if you're to your set temperature, you don't need, your fans will shut off. Your fans shut off after you hit that set temperature.
Awesome. Jasper was asking, does the ventilation fan CFM sizing recommendations that you gave, are those based on climatic region? Like, are there differences between the Midwest, where it's maybe a little bit more humid, and the Southwest that's more arid?
Yeah, well, it's basically based on temperature. So those recommendations for one airflow, one exchange of air, one complete exchange of air per minute for warm weather temperatures would count during any warm during any warm part of the year in any region. So as it gets cooler, those requirements will be diminished. So if your temperatures are, if you're in a region where the temperatures are cooler at certain parts of the year, then it diminishes down during those periods of time to only about a half an exchange of the cubic feet of the tunnel or the greenhouse every minute. So it's based on air temperature, no matter what region you're in. Even if you're in an arid region, it can get extremely hot. So when it's during the hot parts of the year, you're going to need the capacity to have an air exchange of the entire cubic feet of the tunnel up to 8 feet high. This is for greenhouse production. You'll have to exchange that air at once every minute. You'll have to have the fan capacity to do that.
Great, thank you. Jasper, if you're around, did that answer your question?
Yes, thank you.
Awesome. Saw that Randall was mentioning energy efficiency through the NRCS. Chris included that information on one of the final slides about funding. There's programs, and again, local resources might be available to supplement federal funds if you do not see what you would like in some of those funding opportunities. The climate grant through the conservation districts here in New Hampshire would be a great source of funding for geothermal and renewable energy heating. Bob says that newspaper works great to close those gaps. You were mentioning foam, Chris. I think I've also seen the spray foam. I'm not sure if that works. Also seen some of those insulation measures turned into mouse insulation layers.
Yeah, I'm not sure the UV resistance of the spray foam.
Okay, great. That's a good consideration. Let's see. And then Bob has a question. Bob, I haven't read through it, so I'm just going to read your question out loud. This is to Chris. Have you ever heard of any greenhouse operations that might have tried this type of efficiency? He's referring to
the dry perimeter zone. I'm reading
okay, so
it now.
You can see that.
Yeah.
Great. Yep.
Yeah, he's asking about a dry perimeter zone of 15 to 25 feet away from the foundation around the structure. He thinks it's the University of Montana and maybe Finland collaborating. I have not heard of that as a measure. I'm assuming they're trying to remove the moisture so it's not wicking energy or heat from the structure. It makes sense to me. The idea makes sense to me, but I have not seen it. I haven't seen or read anything about that. I'm sorry, I can't answer better.
We'll do some digging. Thanks, Bob. And then I skipped Sue's question about wiggle wire. Just asking what is wiggle wire?
Oh, I'm sorry, I didn't explain that. There's it's a one system to attach. It's a very popular system to attach your plastic to the structure. So there's a metal channel that you screw to the structure where you want to attach your plastic, and drape the plastic over the top of that channel once it's in place. And you use a wire that's kind of bent in an angle, many angles, you kind of wiggle that wire into the channel, and it captures the plastic and holds it in place.
Awesome. Thank you. So Heather has a question. For folks that are still left, if you want to pop off mute, Heather, you can come off mute and ask your question. That'd be great.
Yeah, it wasn't actually a question. I was just commenting on the previous person's question about using a dry zone to improve efficiency. So we know that tunnel soils can pull moisture from the soil surrounding the tunnel. So, you know, would you need to irrigate more if you did something like that? Would just be a question in my head.
Yeah, I think the moisture being pulled usually stays within like 2 or 3 feet of the edge of the tunnel. I mean, that's where it's most contributes to the root zone of the plants. So you would need more irrigation, I think, in those outside beds. Now this is conjecture on my part because I haven't, like I said, read about that system. But it would seem to me that the outside beds would be a little bit drier if you were had a dry zone around the entire tunnel.
Fantastic. Does anybody else have other questions for Chris while we got him on the line? Perfect. Well, thank you again so much. Thank you, Chris. Thank you to everybody who joined today. Like I said, we'll be sending this recording around so you can refer back. I know I will have to do the math over again and appreciate those formulas separately. So thank you again, Chris. Really appreciate it. And we hope to see you in January talking about agri-solar.
Sounds great. I look forward to it.
Fantastic.
Thank you.
Thank you, everyone.
Thank you.